everyone, and welcome to lesson 13 on the Save My STEM Physics channel. This is the last lesson on the the quantum phenomena and particle physics section of the channel, or at least in year 12. And this lesson is about Feynman diagrams. So Feynman diagrams are a way to represent interactions, fundamental force interactions and annihilation and pair production. And yeah, that's about all I've got to say in the intro. But one thing that you need to keep note of, one thing that might not make sense when I first say it, is remember momentum is conserved. Whenever an exam question asks about Feynman diagrams, this will always be on the mark scheme, whether it's whether it's to do with you drawing a diagram, whether it's to do with you answering a question. 99% of the time, it wants you to mention or demonstrate that momentum is conserved. So how do we actually show that in terms of diagrams? Well, there are seven diagrams that I will be going over today, and we will go in order of the fundamental forces. So we'll go strong, weak, and then electromagnetic. There's no gravitational ones that you need to know for A level, or at least as far as I'm aware. So let's just start with the strong interaction. So there's only one Feynman diagram for the strong interaction, and the way every Feynman diagram looks is you have axes, a y-axis and an x-axis, which kind of represent time. So the y-axis kind of represents time, and the x-axis kind of represents space. But for the most part, you can just leave them unlabeled. They don't generally ask for you to label the x-axis. Sometimes it may ask for you to label the y-axis as time. But for the most part, it doesn't matter. And they will all generally have the same shape. So they'll have one particle moving in that direction, one particle moving in that direction, an exchange particle represented with a squiggly line, and then they will have the particles shooting off in opposite directions at the same angle. So this angle here is the same as that angle there. And that is how we demonstrate our conservation of momentum, because they're traveling at the same speed in opposite directions. And so in the strong interaction, what we have, the strong interaction is felt between nucleons, constituents of the nucleus, and therefore is felt between protons and neutrons. So we'll have one proton on the left-hand side and one neutron on the right-hand side, and as they approach each other, the strong interaction becomes repulsive, and it's just as simple as they repel each other and they go in opposite directions. So the proton moves that way and then ends up moving that way. The neutron moves that way and then ends up moving that way. Simple enough. But what is the exchange particle? This is something which you may remember from the exchange particles video, or you might know from from other knowledge, but it is a pi neutral meson, and you will just denote that above the squiggly line, pi neutral. Hopefully you can see that enough, and hopefully that makes enough sense. So the arrows demonstrate which direction they are traveling in, but there is an exception to that, which I believe, will get onto later in the video. Now let's have a look at weak interactions. So this is our beta minus and beta plus. So I'll just do beta minus on this side and beta plus on that side. So we will again get our set of axes. I apologize if this highlighter runs out halfway through. There may be a jump cut if I need to go get a different highlighter. And our beta minus and beta plus decay is going to have a slightly different shape, because there's only one left-hand side, one constituent on the left-hand side of weak interaction. If you remember, for beta minus, one singular neutron decays into 3 particles. So we'll start like that. We'll have our neutron traveling in this direction. Whoops, sorry, you can't see that. We'll have our neutron, N, traveling in this direction. And we will have our boson, and we will have our two so we'll have 2 things formed on this side and then 1 thing formed on this side. So the thing formed on this side is going to be a proton, because the neutron changes from a neutron to a proton. That's because 1 down quark in the neutron changes flavor to an up quark, so that it has a proton quark configuration and is therefore a proton. And then on this side we will have an electron, and I've just realised I've drawn this wrong. Because what happens here is we actually have the exception to the rule that I was just talking about the arrows. So this particle formed here is an electron antineutrino, and it is an antiparticle. So Lord knows why. I'm sorry that I don't know why, but for antiparticles, the arrow is drawn the opposite direction. So it's not actually going in towards the boson. It is still traveling that direction, still traveling out from the interaction. But because it's an antiparticle, the arrow is drawn the other way around. I'm not sure why. I'm so sorry. And we know that in beta minus decay, our boson is a W minus boson. And we will have a very similar thing on the right hand side for beta plus. We will have a proton with a W plus boson. It will decay into a neutron traveling that direction, an electron neutrino. Sorry, that's very unclear, but that says VE, electron neutrino. And that's not the opposite way around because it's a normal particle, but this is the opposite way around because it's a positron that's formed. So these are our weak interactions, that's our strong interaction, and so we have the I like to think about the reactants are on the bottom half and the products are on the top half. Um, like that's sort of like a chemistry way to look at it, even though it's not a chemical interaction. And yeah, so that's sort of how I like to think about it. Now, before we move on to the next part, uh, I just want to talk about how we decipher what boson is going to be used. So the bosons also typically have arrows attached to them. So this boson is moving across the wave like that. This boson is also moving across the wave like that. But how do we know that this is W minus and not W plus? Well, because the neutron, so Q of neutron, charge of neutron, equals 0. But Q of proton equals 1. So how are we going to give it 1 charge? Well, if the boson is moving that way, that means that it's taking charge from the neutron to give to the other side. So if we're taking away charge, we're going to be taking away a negative charge to give it a positive charge, basically. So 0 minus 1, the -1 charge from the W minus boson, gives the proton a charge of 1. Hopefully that makes sense. Another way that you can look at it is just that it needs to take this entire right-hand side has a charge of -1, so it needs to give it a charge of -1 by taking a -1 charge over to it. And the same rule applies to this one, where it's taking a positive charge over, and it's taking a positive charge away from this side. Hopefully that makes enough sense. Because there are exam questions that can ask you what bosons are present in each interaction. We will get onto our. Oh wait, there's one more weak interaction. Sorry, is that a weak interaction? No, that is a electromagnetic interaction, kind of. Not really. Anyway, so electromagnetic interaction. Uh, the simplest one, or well, sort of the only one that's truly and properly defined as electromagnetic, is electron scattering, and it's really simple. It's just an electron moving that way and an electron moving that way, and there's a boson in between them, and there's an electron moving that way, and there's an electron moving that way. Everything here is an electron except for the boson, which we'll get onto in just a second. Everything here is an electron, and they have like charges, and this is the electromagnetic force, so they're repelling each other. It makes sense. They've got the same charges, they've got the like charge, so they're repelling each other. And if you remember from the exchange particles lesson, they have a virtual photon which has a symbol of gamma. So it's just kind of like a Y with a little bend in it, I guess. Um, and yeah, it's really, really simple, is that one. It's just electrons repelling each other when they get too close to each other and moving in opposite directions. Um, and then I guess this kind of counts as electromagnetic because there is an electromagnetic interaction going on here, but it does have a different boson. It's because they're attracting each other. That it's still an electromagnetic, but there's other stuff going on. So I wouldn't put this under the label of EM. This is just kind of miscellaneous. It doesn't really belong to a category. But this is electron capture. Sorry, I forgot to mention this is E scattering, electron scattering. And this is electron capture, what I'm about to draw here. And what it is a proton moving in this direction, with a boson like this, has a neutron moving in this direction, and a electron neutrino moving in that direction, and also on the reactant side of things, so moving into the reaction, is an electron. So all that's going on here is the proton and electron are meeting each other to form a neutron and an electron neutrino. This follows our conservation laws, and the way that we're going to think about what the exchange particle is the proton becomes a neutron, so we need to take charge away from it. So if we're taking a positive charge away, we want this to be a W plus boson. Because 1 minus the positive charge of a boson equals 0, which is the charge of a neutron, Q of N. Okay, and the next interactions also don't really follow a fundamental force, but we have annihilation. Sorry, you can't see that. Annihilation, which I'll just represent as A because I can't be bothered writing it out, and pair production, another one that I can't be bothered writing out. So I'm just going to split it down, and we're just going to have annihilation on the left-hand side and pair production on the right-hand side. So annihilation, again, it follows the same thing for any particle-antiparticle pair. So we're just going to choose electron and positron. Now, interestingly, this one won't have a boson in the middle. But it does have an arrow of the electron moving towards the positron. Now, in reality, in the physics of it, they will both actually move towards each other because they are attracting each other equally because they have opposite charges. But Feynman diagrams are sometimes really stupid, and I don't know why. You just need to draw one of them moving towards the other. And when they meet, you have two photons given off, which the same as virtual photons and real photons both have the symbol gamma, so we have a gamma here and a gamma here, because they're given off in the so the energy released during annihilation is released in the form of photons. E equals mc squared. So each photon will have an energy equal to E. Energy of photon. And pair production is kind of the same. We have, although it takes a very different shape to all the other Feynman diagrams that we've seen, we have one photon here, photon like that, and this will produce two others. It will produce an electron and a positron. Remember that it has an opposite facing arrow because it's an antiparticle, and you can draw this next part on either the electron or the positron, but we have another photon released, which just has leftover energy because this photon might have energy more than the sum of these two masses multiplied by the speed of light squared. So this is just where the leftover energy goes in the form of another photon. And one thing that's very important that you have to know is that this pair production must happen in the presence of a nucleus. That's something that isn't just restricted to Feynman diagrams. That's something you need to know, is that this pair production happens in the presence of a nucleus. And I believe that is the end of the Feynman diagrams lesson. I'm so sorry that it's very long, but there are a lot of diagrams to go through. Thank you very much for watching, and the next part of the course will be waves and their interactions. Bye.